Much for the kind invitation, and it's nice to see that everyone here is safe and healthy. Today I'm going to talk about algebraic approximations of compact Kähler threefolds. So most of the time during this talk, we'll deal with non-algebraic varieties. But as we will see in the study of this problem of the existence of algebraic approximation, it will be crucial to have a good understanding of compact Kähler threefold. So in particular, the bimeromorphic classification of non-algebraic compact Kähler threefolds. So I hope that from this point of view, this talk will fit into the theme of today's workshop. Before I introduce the main statements of the talk, let me start with the Codeira embedding theorem. This is a projectivity criterion proven by Codeira in terms of the existence of rational Kähler class. So the statement is the following: given a complex manifold X, the following two statements are equivalent. The first one is the manifold X is projective, namely it is a complex submanifold inside a projective space. And the second statement is that there is this Kähler form omega on X, such that its Theorem cohomological class sits inside the second cohomological group with a rational coefficient. Here we are not going to work directly with the definition of Kähler form in this talk. However, this is the definition. The Kähler form is just a real two form of type 1, which is closed and positive. So positive in the sense that omega is the negative of the imaginary part of some Hermitian metric. And by definition, a Kähler manifold is a complex manifold endowed with a Kähler form. As examples of Kähler manifolds, we have a projective space, and actually, given any compact Kähler manifold, every complex submanifold of it automatically carries an induced Kähler matrix. So in particular, every smooth projective variety over C is an example of Kähler manifold. So this gives a plethora of examples of Kähler manifold, and these manifold can be regarded as a generalization of smooth projective varieties. There's another way to see that Kähler manifolds are a generalization of projective varieties from the point of view of small deformations. So while small deformations of projective varieties may not remain projective anymore, but small deformations of Kähler manifolds remain always Kähler. For examples of non-projective deformations, we can consider, for example, versal deformations of complex versal deformation of abelian varieties as a complex manifold, or universal deformations of projective K3 surfaces. So there are plenty of these non-algebraic deformation examples. So this makes the following.
Can I ask a very general question? So it's like obvious why projective varieties can deform into non-projective, but can you comment about Kähler deforms to Kähler? So apparently positivity is an open property, positivity of a form is an open property, and what about being closed?
What about being closed? So I think for the moment I'm not, this is not on the top of my head, so I'm not, I think for the moment I'm not capable of giving any comment of this.
Sorry, can I say it again?
So I think for the moment I'm not capable of giving any comment of this about the closeness. Yeah, closeness under deformations of compact complex manifold.
Okay.
This is not in my active memory. Yeah, so this makes the following definition non-trivial. Given a compact Kähler manifold X, an algebraic approximation of X is a deformation of X, here denoted by pi, such that in the base, the subset parameterizing projective member is dense inside the base. So dense with respect to the classical topology. And the so-called Codeira problem asks the following. Given a compact Kähler manifold, can we always find an algebraic approximation of it? And here are some known results about the Codeira problem. Of course, for curves, the answer is always yes, because curves are always projective. For surface, the answer is also yes. And this result was first proven by Codeira based on his classification of compact complex surfaces in the early 60s. Later, Bogdan also gave proof, more intrinsic proof of the existence of algebraic approximations based on Hodge theory, so using a variation of Hodge structures.
I'm very sorry.
Yes.
Can I ask a non-mathematical question?
Yes.
Apparently, there is some technical problem with the sound. So it seems that everything sounds very lowly. So maybe can you speak just a bit louder because.
Sorry.
Yeah, this is perfect now. Thank you.
Okay. So is the volume okay now?
Yeah, now it's totally great.
Okay, so I will try to speak like this. Okay, so let me go back to the Codeira problem. So the so-called Codeira problem asks, given a compact Kähler manifold, can we always find an algebraic approximation of this compact Kähler manifold? Namely, deformations of this manifold such that in the base there is this dense subset parameterizing algebraic members. And for known results, for curves and surfaces, the answer of this problem is positive. But starting from dimension 4 and on, there exist counterexamples to the existence of algebraic approximations. And the first series of examples were constructed by Wazan. And slightly later, Ogiso also constructed an example using a different technique. And actually, what Wazan constructed is compact Kähler manifolds whose homotopy type is not the homotopy type of any projective manifold. So in other words, there is this effective homotopical structure for a compact Kähler manifold to be projective.
And can you comment about the surface case? So apparently, when you refer to Codeira, I guess that you mean that this is explicitly contained in Codeira Enriquez classification, right?
Yes, yes.
And then what's the second reference? So is it just classification independent?
No,
I mean,
yes. So Bogdan's proof doesn't use the classification result of Codeira. So what he shows is so his proof relies on density criterion due to Green in terms of variation of the whole structure.
Sorry, please. Well, the same problem again. Can you speak louder?
Yes. Can you hear me now?
I think that now it's better. Yeah.
Now it's better.
Thank you.
Okay. So yes. So Phil, don't hesitate to interrupt me if you cannot hear me well again. I'll try to speak louder. Yes. So the point of Bogdan's result is that the starting point is that if we have a deformation of a surface S like this, then we can look at H11 of ST. So this will be a subset which varies inside H2 of S. And then Bogdan has used density criterion due to proven by Mark Green. So which is the criterion guarantees that when we consider the variation and the variation of the H11 inside this vector space, when does it encounter a rational point, a rational class inside H2? Yes, so as long as we have, as long as the Kähler cone encounter a rational class, then by her Codeira embedding theorem, we know that this fiber will be projective. So by her theoretic proof, I mean Boda's proof is based on this Green's density criterion. So today we are going to focus on the case of threefolds, and the main result that we are going to discuss today is that every compact Kähler threefold has always an algebraic approximation. So before but we can also consider a weaker version of the Codeira problem, namely what he asks is given a compact Kähler manifold, can we always find a bimeromorphic model of the compact Kähler manifold which emits an algebraic approximation? And the bimeromorphic version of the Codeira problem was solved for threefolds with a Codeira dimension 0 previously by Patrick Gaff. About the proof of this result, it also relies on the bimeromorphic classification of non-algebraic compact Kähler threefolds. So we might wonder whether there is some subclasses of compact Kähler threefolds whose existence of algebraic approximations can be generalized to arbitrary dimension.
And can you comment about the result of graph? So what's the bimeromorphic Codeira problem? Does it ask for small deformations which are bimeromorphic to which are motional?
Yeah, the precise statement that he proves is that so given a compact Kähler threefold with Codeira dimension 0x, we can always find a bimeromorphic model. So a compact Kähler threefold, which is bimeromorphic to x, such that this manifold has a flat deformation, and such that over the base, inside the base, we can find a tensor subset parameterizing moishes and fibers.
I see.
Yes. So this is the bimeromorphic, the so-called bimeromorphic Codeira problem. So in order to state the following result, let me first recall the definition of algebraic dimension. So given a compact complex manifold, the algebraic dimension of X, generally denoted by A of X, is defined to be the transcendental degree over C of its field of meromorphic function. And this is an integer between 0 and the dimension of X. And when the algebraic dimension is maximal equal to the dimension of X, we call this manifold Moishesan. And the Moishesan's projectivity criterion asserts that for a compact Kähler manifold to be projective, it is equivalent for it to be Kähler and Moishesan. So according to this projectivity criterion, for compact Kähler manifold, which are non-projective, the maximal algebraic dimension will be the dimension of X minus 1. And actually, when X is a compact Kähler manifold, such that such that we have the equality, namely when the A of X is equal to the dimension of X minus 1, then we can also show that it always has an algebraic approximation. And more concretely, if we look at the algebraic reduction of such compact Kähler manifold, then it is always bimeromorphic to an elliptic vibration over a projective variety. And previously, in the joint work with Benoit Claudon and Andreas Erhing, We also prove a binomial version of this statement. So namely, a given complicated manifold as in the statement, we can always find a binomial model of it, which has an algebraic approximation.
And can you comment too? Do I understand that correct that the Bimeromorphic version, so the black assertion is weaker than the blue assertion, right?
Yes, so the binomial version is weaker
Yeah.
than the original version, right?
So it's not a development from top of the page to the bottom of the page, but a kind of historical comment. And
yeah, so it's
the blue theorem is stronger.
Yeah, it's more like a historical comment. Yes. And before we talk about the proof, let me mention some consequence of the existence of algebraic approximations. First of all, is the following corollary saying that actually, when we allow under the same condition as in the main statement, the algebraic approximation also exists when we allow rational singularities. So the corollary states that whenever we have a complex variety with at most rational singularities, and assume that it is binomiorphic to a complicated manifolds, then we assume that it is in the Fujiki class C, and assume that it is either a threefold or of algebraic codimension 1, then this complex variety also has an algebraic approximation. So here, in the sense that X has a flat deformation such that in the base, the Murchison members are dense in the base. And here's the proof of this corollary, assuming the main theorem. So since X is in the Fujiki class C, we can find a binomorphic morphism from a complicated manifold X tilde to X. And since X has rational singularities, so we have the vanishing of the higher push forward of the structure sheaves. And by a result of a run, so these two conditions guarantees that deformations of X tilde will induce deformation of the binomiorphic map F. So, and since we know that under these conditions, X tilde will have an algebraic approximation, and this will imply that X will also has an algebraic approximation. And it is also clear from the existence of algebraic approximation that if X is as in the main statements, then the invariants of X that are preserved under small deformations, such as the fundamental group or the Hodge diamond of X, can also be realized by some projective manifolds. And again, previously, in the case of fundamental group, this was also proven in the same joint work with Benoit Clodon and Andreas Erhing. So without knowing fully the existence of algebraic approximations. Now let us talk about a general approach to find an algebraic approximation given a compact Kähler manifold. So now that X be a complex manifold and that X prime be a bimeromorphic model of it, a question that we would like to ask first is that when does a deformation of the bimeromorphic model X prime induce a deformation of X? And here is one situation where this happens. So given a resolution of this bimeromorphic map, so denoted by this diagram, and let nu be the binomorphism from the roof X tilde to X prime, and then we assume that X tilde is smooth. And that is also given a subvariety Y inside X prime, such that this subvariety contains the locus which is modified under the map nu. So namely, outside of the subvariety y, nu induces an isomorphism between x tilde and x prime. So assume that we have a deformation of x prime like this, and assume that inside this deformation, we can find, so assume that this is the subvariety y, and also assume that we can find a neighborhood of y inside the x prime, such that this neighborhood deforms trivially inside the deformation of x prime. Then by replacing the blue part of this deformation by the trivial deformation of the total transform of this neighborhood under the inverse of nu, then such a deformation of x prime will induce a deformation of x tilde. And then by the same argument involving Ran's result, deformation of x tilde will also induce a deformation of x because x is smooth.
So I'm a bit lost with Ran. So did he assume something on the morphism? So did he assume this rational singularity property?
So Ran didn't assume the rational singularity property, but only these two conditions.
Yeah, but do you have the second one in the case downstairs?
So in the case downstairs, yes, because x is smooth.
Ah, sorry, yeah, you're already in the smooth. Yes, I understand it. And so, and basically, the result of Ran is that, so if you have a morphism like this, then whenever you deform the source space, the target space also deforms.
Right, right. So this is what Ran calls a source stable result.
I see. Thank you.
Whenever we have this vanishing of R1 push forward, and also whenever we have this, then deformation of the source always induce deformation of the map. So so what I mentioned before can be So here is the mathematical statements about what I mentioned before.
But sorry, once again, can I ask another question about Ran? So but he doesn't claim. Am I right that he doesn't claim that if you start with x twiddle and x, and you have a contraction from x twiddle to x, then it will deform into something similar. So it maybe will deform into something like an isomorphism.
Yeah, I don't think he claims this, but only that only that the map deforms. Yes. So
it's possible that in the central fiber you have a non-trivial morphism, so you really contract something, and in a neighboring fiber you have a trivial morphism, so like you don't contract anything.
So I think I think it is possible because the only thing that we know is that there is this say a deformation. Say if x tilde is a deformation, this fat x tilde is a deformation of x tilde. Then under this assumption, we know that there is this deformation of x, and the map between them such that f, such that this is an extension of the original map f.
Yeah,
So
I think I understand.
I think what you mentioned could happen. Okay, so let's continue. So in order to make a mathematical statement of what I mentioned before, let me introduce the following notion of y locally trivial deformation. So if y is a subvariety of x, and we call the deformation of x y locally trivial, if we can find a neighborhood, open neighborhood of y, which deforms trivially in this deformation along the base delta. And from what we saw before, Yeah, it is not difficult to see that whenever the binomial model of x prime is normal, and assume that this x prime has a y locally trivial algebraic approximation for every subvariety y of x of codimension at least 2, then the original compact manifold will also has an algebraic approximation. And there is this similar statement where neighborhood here is replaced by a formal neighborhood. So which means that the completion of x along the subvariety y. So the main results now are reduced to the following. Given a compact Kähler manifold x, and first of all, assume that the dimension of x is equal to 3, and the algebraic dimension is less than or equal to 1. So the approach we prove the existence of algebraic approximation of x is to first find binomial model of x prime, such that it is normal, and such that we can find an algebraic approximation of x prime, which is y locally trivial for every subvariety y of dimension less than or equal to 1. And when in the case where the algebraic dimension of x is equal to the dimension of x minus 1, it turns out that it is too much to ask that there is this such binomial model having a y locally trivial approximation. And instead, what we prove is that we find first, again, a binomial model x prime of x, such that it has an algebraic approximation which is formally y locally trivial. So where y is a subvariety containing the locus, which is modified by the inverse of nu. And today in this talk, I will only focus on this part of the proof. And for the case of algebraic codimension 1, this will be another subject. So yes, so to sum up, we decompose the proof into two steps. So the first one is to first find a binomial model of x, so which is possibly simpler and more concrete to study. But the trade-off is that we need to find a more precise version of the existence of algebraic approximation for this for this nice binomial model. And let us start with the first part. So I will explain to you how which kind of binomial model we consider to study this Codeira problem for threefolds of algebraic dimension less than or equal to 1. So here is the binomial classification of non-algebraic compact Kähler threefolds. So non-algebraic compact Kähler threefolds has algebraic dimension 0, 1, or 2. And when the algebraic dimension is equal to the dimension of x minus 1, then we already mentioned that x is always binomial to the total space of an elliptic vibration over a projective manifold. And now, given a compact Kähler threefolds, we have the following classification results for threefolds of algebraic dimension less than or equal to 1. And first, let us assume that our threefold is non-uniform. And this classification result is essentially due to Fujiki in the 80s. So let X be such a threefold, then we can always find a binomial model of X satisfying one of the following description. So the first description is that X prime is the quotient by a finite group of either a 3 torus of algebraic dimension 0 or the product of a k-trivial surface of algebraic dimension 0 with a curve. And moreover, this finite group action acts diagonally on the product. And the second possibility is that X prime is the total space of a vibration whose general fiber is 2 torus, and the vibration is without multisection. And moreover, if the fiber F is non-algebraic, then actually this vibration is a quotient by a finite group G of a G equivariant fiber bundle in 2 tori. So namely, this is a quotient of a G equivariant smooth isotrivial 2 torus vibration. So I say that this result is essentially due to Fujiki, and the only input of the Kähler minimal model program for threefolds due to Campana, Ergin, and Pinternet is to rule out the existence of a simple non-Kummer threefold, so which was originally which was not excluded by Fujiki's result. Now let us look at uniroot case. For uniroot non-algebraic compact Kähler threefold, up to bimeromorphic modification, we have one of the following description. So either this threefold, either X is bimeromorphic to a P1 bundle over a smooth compact Kähler surface of algebraic dimension 0, or it is a total space of a P1 vibration over an elliptic surface S over B. And moreover, if we look at the general fiber of this composition, so the composition of the P1 vibration with the elliptic vibration, then general fiber will be a roof surface, of course, over an elliptic curve, and with an invariant E equals to 0. So this invariant is the invariant of the roof surface in Harshon's book. And this result is due to Fujiki. For non-algebraic uniroot threefolds, so what is clear is that X has a cannot have non-tree. Yes. So what is clear is that X has non-vanishing H20. So from this, it is easy to see that the base of the MRC vibration is always a surface. So namely, X is always a bimeromorphic to a P1 vibration and over a non-algebraic surface. And actually, the description number 4 corresponds to the case where the base has algebraic dimension 0, and number 5 corresponds to the case where S has algebraic dimension 1. And let me provide a sketch for the implication that if the base of the MRC vibration has algebraic dimension 0, then X is always bimeromorphic to P1 bundle. So first of all, we have following a result due to Sakizov and extended to the non-algebraic case for threefolds over for the threefolds. We can assume that this P1 vibration is a standard conic bundle, and again with the surface a non-algebraic surface. And here a standard conic bundles means a conic bundles F between from X prime to S, such that both X prime and S are smooth, and such that this conic bundle has S simple normal crossing discriminant divisor. And moreover, we ask that for every irreducible divisor D inside S, so here for every irreducible curve, the preimage of D under the vibration F is irreducible. So this is the same to saying that the Picard rank upstairs is equal to the Picard rank downstairs plus 1. Next, we have the following result due to Bobby. So Bobby shows that for a such standard conic bundle, if we take irreducible component of the discriminant locus C, then the variety of lines above C is connected 2-to-1 cover C tilde over C, and such that the branch locus of this 2-to-1 cover is equal to the intersection of C with the residual component of delta to C. This implies in particular that if C is a rational curve, then the intersection of this component with its residual component to the discriminant divisor contains always at least 2 points. And for a surface of algebraic dimension 0, we know that, so as a consequence of Hsueh-Yung theorem, such a surface only has finitely many curves. And moreover, these curves are always a disjoint union of finite disjoint union of ADE curves. And in particular, these are a finite disjoint union of trees of P1s. So given a curve inside S, its irreducible components are all rational, smooth rational curves. And since this belongs to a tree for P1s, we know that necessarily it contains irreducible components whose intersection with the residual component has at most 1 point. And this contradicts this inequality, which implies that in particular the discriminant locus of the standard conic bundle is necessarily empty. So this implies that whenever we have a standard conic bundle over surface of algebraic dimension 0, then this standard conic bundle is always a P1 bundle. According to the classification result, let me summarize by stating the theorem that which will imply the existence of algebraic approximation of the threefold that we consider. So to prove the existence of algebraic approximation, it suffices to prove this statement. So saying that up to replacing x prime by a binomial model of it, then x prime as in the above list, the description number 2 to 5, this threefold always has a y locally trivial algebraic approximation for every subvariety y of dimension at least at most 1. So for the rest of the talk, I will try to give an overview of the proof of this theorem prime according to the description of x prime from the above list, number 2 to 5.
Can I ask you for a general comment about this y local triviality property?
Yes.
So, according to your theorems, there is some difference in this step for from the one hand, in the case when the algebraic dimension is small, and from the other hand, in the case when the algebraic dimension is the dimension -1, and the assertion for dimension -1 is weaker, right? You don't claim that you can deform an actual neighborhood trivially, but you only claim that you can deform a formal neighborhood trivially.
Yes, yes.
And so what should be the intuition here? So, for instance, suppose that you take a variety x which is already projective.
Yes.
What can you say about its y locally trivial deformations?
Yeah, so maybe let me explain why it is too much to expect the existence of a wide locally trivial algebraic approximation in the case of algebraic codimension 1. So as I say, in the case of algebraic codimension 1, X is bimeromorphic to elliptic vibration. So over some projective base. Yes. So so assume that we have a curve, say C inside X prime, which is not contracted by this vibration. So we will obtain another curve, this image inside B. So yes, and for instance, I think it is too much to expect that there is this we can find a neighborhood of this C prime such that we have an algebraic approximation of X prime, and which doesn't changes this f minus 1 u. So so this is because, for instance, if C prime is ample inside of B, then we can deform slightly a little bit. Assuming that C prime is very ample inside of B, then we can deform a little bit C prime to have a neighborhood of to have a neighborhood of C prime inside B. Then but if for every perturbation of a C prime, say C prime prime, since X is not algebraic, actually, if you look at the elliptic surface over C prime prime, it will not have a section, because if it has a section, then by her Campana's projectivity criterion that I'm going to mention below, the threefold X prime will be algebraically connected in the sense that given any 2 points, we can find a connected curves containing these 2 points. So so from this, you see that it is in this case it is too much to ask that for instance the preimage of this neighborhood U remains deforms trivially inside the algebraic dimension, algebraic approximation of X prime, because if it deforms trivially, then above this C double prime, the elliptic surface will not have a section, and which cannot happen because which contradicts the existence of algebraic approximation.
Maybe I see what you mean.
Yeah.
So basically informally it's something like the larger the algebraic dimension is, the more deformations you can allow, and
yes,
the more difficult it is to keep track on.
Yes, or put it another way is, if the algebraic dimension is higher, then we will have more sub-varieties inside the manifold that we want to study. And why? Yes.
Returning to low algebraic dimension. Do you actually prove that? Suppose that the algebraic dimension is small, and then you have some sub-variety y. And is it true that any deformation of X is y trivial or not?
So for the moment, I don't have For the moment, I don't have such general result which works in arbitrary dimension.
But at least, do you know the reason why it should fail? For instance, does it have a chance to be true?
I think for higher dimension, the geometry is still not so clear. So yeah, the advantage of threefold is that I think the geometry is quite clear from either the MMP or from Fujiki, Fujiki's results that we see here.
Mhm.
And we see, for instance, in this case,
Yeah, let's assume that the algebraic dimension is 0. Oh, sorry, 1. Yeah, 1.
Yes.
Great.
Yeah, less than or equal to 1. And in this case, we see that yes, basically, for surface of algebraic dimension 0, we only have finitely many curves.
Mhm.
So basically, subvarieties of this the quotient of this product can be completely described. So this is why we can in these cases we can we can actually how to say, we can actually describe in some cases we can actually describe what are the subvarieties of the threefolds of dimension less than equal to 1.
So just to summarize,
Yes.
let's assume something. Let's assume as much as possible. For instance, that the dimension is 3, and the algebraic dimension is either 1 or 0, or whichever is better, whichever is stronger from any point of view. So you claim and you proved that there exists y locally trivial approximation, well, y locally trivial deformation. But can you expect, do you feel it reasonable to expect that any deformation becomes y locally trivial in this case?
In some cases, yes. So in some cases, in some cases there exists an algebraic approximation such that this is y local trivial for any subvariety y. So for instance, yes.
I'm asking not about existence, but about can you change the existence to any if you assume, say, dimension 3 and algebraic dimension 0 or something?
You mean any algebraic approximation is y locally trivial, something like this?
Yeah, the question is, can you expect something like this?
I think this is still too much to this is too much to also too much to ask. So so y locally trivial in particular, it will preserve the subvariety of y, and I think this is a very strong property. For instance, if you try to deform say two torus, your non-algebraic two torus but emit an elliptic vibration, then there are ways of deforming this elliptic vibration while not preserving this vibration structure.
Mm-hmm.
So I think asking that any algebraic approximation preserves subvariety is even this is too much.
I see. You just deform it to something of algebraic dimension 0, and then it's not preserved.
Yes.
Yeah. Thanks a lot. Thanks a lot. Now it becomes more clear.
Okay. So since it remains only 10 minutes, I will only choose some cases to explain the existence of algebraic approximation. So let me skip the case number 2, which is for me, I think the most approachable one. And then let's start with the case number 3, which concerns torus vibration. So before talking about case 3, so let me start with the following important projectivity criterion due to Campana. So Campana's theorem says that given the compact Kähler manifold, being projective is equivalent to being algebraically connected. And here, a manifold is called algebraically connected. As I said before, if for every general pair of points x and y inside x, there is this connected proper curve C, which contains both points x and y. And let me recall the description number 3 in the classification result. So in the classification, in the description number 3, the threefold X is bimeromorphic to threefold X prime, such that it is the total space of a vibration whose general fiber is 2 torus, and such that the vibration is without multisection. And moreover, if the fiber is non-algebraic, then it is the quotient of a fiber bundle in 2 tori by some finite group acting equivariantly. So let us first discuss about the second situation. So let's discuss more generally the case of smooth torus vibration. So given a smooth torus vibration F, first we want to construct some deformation of this vibration F. Let J denote the Jacobian vibration associated to the torus vibration, and that curly J be the sheaf of local holomorphic sections of the Jacobian vibration. And this sheaf sits inside this exact sequence, so which can be considered as the quotient of this Hodge bundle by the underlying integral local system. And here G is the relative dimension of vibration. And every smooth torus vibration is a torsor under its Jacobian vibration. And we know that the set of J torsors are in one-to-one correspondence between with the H1 of with coefficient in curly J. And the image of the smooth torus vibration F inside this H1 will be denoted by A dot or F. And moreover, inside, if you consider the subset of J torsors emitting a multisection, then its image under this one-to-one correspondence will be the torsion part of the H1. And we would like to construct the deformation of the smooth torus vibration F as a family of J torsors. And this such a family actually exists and can be described as follows. First, let this map X to be the map induced by this short by the map exponential map from this curly E to her curly J. And this family will be a family parameterized by the vector space V. And for every point T inside the base, it parameterizes the J torsor, which corresponds, so under this one-to-one correspondence, to the element A dot RF plus exponential of T. And this family pi is called the tautological family associated to F. And this tautological family satisfies the following density property due to Benoit-Claudon. And what it proves is that assuming that the base is compact and assuming that the total space of the vibration is Kähler, then inside the base V, the subset parameterizing vibration having a multisection is dense inside the base. And the construction of tautological family and the density result can be generalized to the G-equivariant setting. So this is again due to Claudon. And another remark is that the tautological family also satisfies some locally trivial property. The last remark is that so if we look at a vibration like this, and if we assume that the base and the fibers are both algebraic, then this result, together with Campana's projectivity criterions, implies that the tautological family will be an algebraic approximation of X. And in the case of description, the second case of description 3, so what we prove The statement that we prove, which implies theorem prime for x prime, is the following. So given a G equivariant fiber bundle, tilde, in the two torus T, without a multisection, we can always construct a G equivariant C locally trivial algebraic approximation for every subvariety C of dimension at most 1. So let me skip the sketch of the proof, but roughly speaking, the construction of the deformation is based on the tautological family of various elliptic vibration and torus vibration. And in the first case of the description number 3, we have a vibration in a median variety over a curve, which is not necessarily smooth. And in this case, we also have an analogous of tautological family associated to this vibration in median varieties, which we prove that this is an algebraic approximation of the vibration. And moreover, this algebraic approximation is locally trivial over B. And this implies this corollary, which implies the theorem prime for the x prime inside the description number 3. So finally, let me mention what happened for unirule threefolds. So recall that the binomorphic description of non-algebraic linear threefolds is either a P1 bundle over a surface of algebraic dimension 0, or a P1 vibrations over an elliptic surface. So let me take maybe 5 more minutes to explain what happened if we are in the situation 4. So given P1 bundle F over S, so by the Campana's criteria, we see that the total space is algebraic if and only if the base is algebraic. And let us assume that the base has algebraic dimension 0, as in the case number 4. The statement that we prove, which implies a theorem prime for x prime inside this description, is that we prove that for such a P1 bundle, there exists an algebraic approximation of S, which leads to a deformation of the P1 bundle F, which is moreover F minus 1C locally trivial for every proper subvariety C inside S. So while not every P1 bundle is the projectivization of vector bundle, it is always the projectivization of some twisted vector bundle. So instead of studying the deformation of the P1 bundle, actually what we study is the deformation of the pair S together with the twisted vector bundle E of rank 2. And the deformation obstruction theory of twisted vector bundle actually parallels well to the untwisted case. So here is what we use to construct the deformation of the pair S together with E. So part of the deformation obstruction theory of E is governed by the Itia class of the twisted vector bundle, so which is the extension class of the first jet bundle associated to E, so which is an extension of the twisted vector bundle E by E tensor omega 1 S. And the following this proposition, so in the untwisted case is classical, and with a similar proof, it also generalized to the twisted case. So the proposition says that assume that the trace map, or also known as the semi-regularity map, is injective, and assume that the trace of the interior class, so the trace contracting this E, so remains of type 1, along a deformation of the surface S. Then the deformation S actually leads to a deformation of the projectivization of the twisted vector bundle E. And let us assume this proposition, and then let me provide a sketch of proof of this theorem, assuming that the twisted sheaf doesn't have any subsheaf of rank 1. So if E has a subsheaf of rank 1, then the projectivization of E is always isomorphic to the projectivization of some untwisted vector bundle of rank 2. And this vector bundle of rank 2 will be an extension of two rank 1 sheaf, and the proof will be different. But let me sketch the proof when E is really a twisted sheaf. So first of all, let pi S be an algebraic approximation of S, preserving the whole neuron summary group, in the sense that each of the class remains of type 1 along the deformation of S. So in particular, this deformation will preserve the trace of the interior class, which lives inside the intersection of H11 of S with H2 of Q. And under the assumption that the algebraic dimension of S is 0, actually we can prove that the trace map is an isomorphism. So this is because, first of all, if you look at the dual of the trace map by serial duality, this is a map induced by the inclusion of O of S into the endomorphism of E. So this map is always injective. And then by assumption, E doesn't have any subsheaf of rank 1. So E doesn't have any non-trivial torsion-free quotient. This implies that if we look at the determinant map from the home space, from this home space to the space of scalar, and which is isomorphic to C, because S, the minimal model of S is either a case resurface or a torus. This assumption implies that the preimage of 0 is the only positive that the determinant is 0 is that the original morphism is already 0 morphism. So since this is isomorphic to C, this implies that this home space is one-dimensional, and this is also equal to the dimension of H0 of omega S. Again, because S is bimeromorphic to her case resurface or her two torus. And this shows that the trace map is isomorphism. And then using these two property, we can conclude by the above proposition that that the deformation of S leads to a deformation of the P1 vibration. So since I'm already over time, let me stop the talk here. Thank you for your attention.
Thank you. Question? Thank you.
Yeah, thank you for. Are there any questions?
I have a question.
Yes.
Can you explain a little bit where did you use the Kähler minimal model program for threefolds?
Yes. So actually, the only place that we use the Kähler minimal program for threefolds is to rule out simple non-Kummer threefolds in Fujik's classifications. So apart from this, nothing is used from the Kähler minimal model program. Yeah, of course, when I first studied this problem, the Kähler minimal program serves for me as an important heuristic guide to understand the geometry of threefolds. But actually, it turns out that much could have been done after Fujiki's classification.
So did you mean your X prime in your this theorem is the minimum is the end product by running the minimal model program? Is the minimal model?
Not necessarily, because for instance, in the description number 3, I only say that X prime is the total space of the vibration, whose general fiber is a 2 torus. But I didn't. So, but from this description, we don't know any minimality about the total space. So there is no description about the netness of or the relative netness of the vibration over the total space from Fujiki's result. And actually, in the proof, while proving the existence of algebraic approximation of X prime, we don't need to know whether X prime is minimal or not.
So your F here in 3 may not be a Fano contraction, something like that.
No. So a priori, this S prime is not. There's no description about whether it is minimal
Okay,
or
thank
not.
you.
Other questions?
I have a question, maybe a general one. Kostya already asked, how about dimensional generalizations? For example, do you hope that some kind of those variety which have algebraic approximation can be somehow described?
So the only
something like this.
So the only result that is known in arbitrary dimension. So apart from the case of algebraic codimension 1, another case is the case of vibration in abelian varieties over a smooth curve. So in this case, we also know that for every compact Kähler manifold which is bimeromorphic to vibration in abelian variety over a curve, it also has an algebraic approximation. So I think an interesting question to study is, given vibration in abelian variety over an arbitrary projective variety, can we find, so up to a bimeromorphic modification, can we find an algebraic approximation of it?
Yeah, by abelian variety, you really mean abelian variety, not just torus.
Yeah, so projective complex torus, yes.
Sorry, once again?
Torus.
Projective complex torus.
Projective complex torus.
Yes.
Yeah, I see.
And about higher dimension, there are at least 2 questions about the existence of algebraic approximation. The first one is that is it true that can we prove or disprove the existence of algebraic approximation for compact Kähler manifolds of high algebraic dimension? So precisely when the algebraic dimension is bigger, is greater than or equal to the dimension of x minus 3. So I think now for the moment, every counterexamples to the Codeira problem all has algebraic dimension less than equal to dimension of x minus 4.
So the hope is that if the algebraic dimension is greater or equal than dimension minus 3, then you have a small dimensional vibration over a projective base.
Right.
And then you try to assemble something from the fiber and the base.
Right. Yeah. So I should say from the algebraic reduction, we will have such a vibration. And for the fibers, we know the existence of algebraic approximation. And now is the problem is kind of whether we can how to deform this vibration in order to have an algebraic approximation. yeah, at least bimeromorphically answer this question.
And maybe,
Actually, interesting question maybe. How about this property to have algebraic approximation? What do you expect? Is it typical or is it something sporadic?
So this is hard to say because so it's only in when the dimension is equal to 3 that we have concrete geometric understanding of this manifold. And also another thing is that for threefold, actually the proof goes through the classification. So far there's no unifying proof proving the existence of algebraic approximation. So I would say that at least for threefold, for me it is more like it's more like an accident rather than But in the case where the algebraic dimensions is equal to the dimension of x minus 1, then we have a unifying proof about the existence of algebraic approximation.
And maybe I want to ask a very closely related question.
Yes.
So let's go to dimension 4. Then
yes.
the example of Voisin and maybe Aguirre, they are all of algebraic dimension 0, right?
Yes.
Because otherwise,
yes.
So, and what kind of, can you comment a little bit on the nature of this example? So suppose that you try to mimic your proof in the particular case of the example. So you know in advance that the proof will fail. So which particular step of the proof is going to fail?
Now, this is a very good question. So, so both Voisin and Aguirre example starts from self-product of, so for Voisin it's self-product of two torus, and for Aguirre it's self-product of K3 surface. So, so what we'll feel is that we will have, so product of two torus can be regarded as two torus vibration over two torus. So I think in this case, in both situations, there are some sporadic subvarieties of dimension 2 inside the manifold. So in the case of, for instance, in the case of Aguirre examples, the way he constructs is to start with a K3 surface, a non-algebraic K3 surface with a very particular automorphism, which cannot exist for projective K3 surface. So what he do is he take the product of this K3 surface and then he blow up the graph of this automorphism and also other subvariety in order to rigidify the deformation. So that any deformation of the K3 surface will, of such manifold, will induce a deformation of the pure K3 surface together with this automorphism. So this is how he constructs these counterexamples to prevent such a blow up of self-product of K3 surface to deform to a projective manifold. So in both cases, there are some sporadic two-dimensional subvariety which prevents the manifold to deform to a projective ones. And yes, so I think in the case of vibration, for instance, in the case number 3, yes, so in good situation, actually, the spatial fibers, the subvariety Y actually all contains in the fibers of the vibrations. And if this subvariety is contained in the fiber of the vibration, and if we know, for instance, the vibration has a locally trivial deformation over the base, then by definition, locally trivial over the base means that we can deform the vibration by just deforming how we clue locally the vibration. So this implies that for every subvariety inside this threefold S prime, automatically locally trivial deformation over the base implies y locally trivial for every subvariety y. And for this, for the case of the fourfold, there might be some sporadic horizontal subvariety which we cannot control. Yeah, in the sense that it's maybe too much to ask that there is this algebraic approximation preserving a neighborhood of such sporadic subvariety.
Okay, thank you. So are there any other questions? If not, let's thank the speaker again. It was really a very amazing talk. Thank you. So we are